Today we want to keep talking about conditional convergence opposed to absolute convergence or divergence, sitting in between. Absolute convergence is a stronger condition. Conditional convergence is the weaker kind of convergence. And we needed to see why that is the case. We can think of conditional convergence as the series needs all those negative terms to get convergence. The terms are going to zero, their terms are decreasing and decreasing to zero, but we need the alternating to get us to convergence. So, to see one of the weaknesses of conditional convergence, we looked at a conditionally convergent series. We looked at the alternating harmonic series. It's conditionally convergent. It converges by the alternating series test, but if we take the absolute value of all the terms, we get the harmonic series, which we know diverges, which we saw with the integral test. So 1 over n diverges, but the alternating over n converges conditionally. So yesterday we did some shenanigans. We did some algebra on the alternating harmonic series. Since it's convergent, this series has some sum. One of the things that we know about convergent series is that if we multiply by a non-zero constant, the series stays convergent. Moreover, the interesting part is that if I multiply all the terms by a half, I'll cut the sum in half. That's an important thing that we have to recognize. It's something that we would assume happens anyway, but it's not enough just to hope that that happens, even if we hope really hard. We're going to need like a whole training montage, some 80s rock music to make this work. But that's still the result. Multiply by all the terms of a convergent series by a constant. The series still converges, and the sum is that constant times the original sum of the series. The next thing we did was we took two convergent series and added them together. Moreover, the sum of the sum series is the sum of the series, the two convergent series. So I can take this convergent series, the alternating harmonic series, and this other convergent series, half of the alternating harmonic series. If I add them together, the resulting series is still convergent. So this is still convergent. Moreover, the interesting part is that the sum is just the sum of the two series. So if I add these two series up, I can add up their sum. This is all just stuff that we know about convergent series. These are not trivial facts. This is how we would assume that it worked. That's what caused problems. We just started assuming that even at infinity, all this stuff will still work. Then we had to do a lot of work to make sure that that was the case and find out when and when it was not the case. So everything looks fine, except for this. All we've done by doing this process is rearrange the terms of the alternating harmonic series. All we have down here is just a rearrangement of the terms of the alternating harmonic series. All the odd denominator terms show up just as they are because that's where I put in all those zeros. The even number terms alternate between canceling out and adding together. Then they cancel out, then they add together. Then they cancel out, then they add together. All the odd terms are where we would expect them. Even terms are alternating, canceling out, and adding together. The result, all the terms in this sum series are in the alternating harmonic series. All we've done is rearrange the terms of the alternating harmonic series. All we have there is a rearrangement of the terms of the alternating harmonic series. The problem with that is that all we've done is rearrange the terms of the alternating harmonic series. We've changed the order of addition, and that changed the sum of the series. We were able to rearrange the alternating harmonic series into a different sum. If the sum of the alternating harmonic series was 10, the sum of the same terms, add them all up, and now we have 15. With a conditionally convergent series, the order that you add things will matter. We're not used to that happening. A plus B is equal to B plus A. Addition is supposed to be commutative. Here's a case where our addition, even though they're just numbers, is not commutative. Addition is supposed to be commutative. You don't change the sum by changing the order that we add things. If I have $5 and you have $7, together we have $12. It's not like, well, if I give you $5, you'll have $12, but if you give me the $7, suddenly I have $4. The order doesn't matter if we have a finite number of terms. Addition is commutative in a finite sum. If you have a finite number of terms, no problem, your addition is commutative. When we have an infinite number of terms, then it depends. If we have a conditionally convergent series, the order matters. Question?
So it's for a finite sum, the terms. It wouldn't add. It would add something different in a finite sum than.
Oh, no. I mean a finite number of terms.
Or sorry, finite number of terms.
Yeah.
Because, but since it's a, so basically the thing is that because it's a repeating, it's a repetition of the first thing that we had, if it's going to infinity, it's still going to be, because what you're getting equal to is what you started with. That's why it's
The addition, yeah, the issue with the addition is all I've done is change the order that we're adding things, but this sum is different than what we started with. Whatever we started up with this, by rearranging the terms this way, we end up with half again as much as you started with,
even though it's the same.
even though it's the same term.
Yeah.
And that's weird. It's also a little bit suspicious when I'm referring to the commutative property in an infinite series. But so it's a little bit fishy that I'm doing that, but I'm doing that because commutative has to do with the order. And we've just changed the order of the terms in an addition problem. An addition is not commutative in a sum, well, in a conditionally convergent. The upgrade is absolute convergence, where things go back to being nice and commutative. The first one, that's the addition that we're used to. We've got a finite number of terms. It doesn't matter what order we add them up, because addition is commutative. But when we're looking at this conditionally convergent series, if we change the order of the terms, we will get a different sum. So when you're looking at a conditionally convergent series, that means there's going to be a finite sum of all those terms. Someone might ask, what is the sum of this series? And you can just say, well, it's conditionally convergent. What do you want the sum to be? And you can make it that. Any questions? Comments? So here's one of the things that we should take away from this little tidbit. The things that we count on, the things that we assume to be true, the things that we believe, the more we believe them, the harder it is to question, which means it's more important to question them. It would be really easy for us to have the facts before we got to this, to just assume that if we didn't have conditional convergence and absolute convergence, we just said, convergence and divergence, that's it. It would be really easy to think that the same rules apply because it's still just addition, right? The same rules apply. It doesn't matter what order we add things up in. But then we start to notice some problems. It's like, well, if we have an infinite number of terms, sometimes the order matters and sometimes the order doesn't matter. We need to be able to figure out what's going on. For the most part, when we're studying this, it doesn't really matter that much because when I write this alternating harmonic series this way, I am specifically telling you to do this order. To say 1 minus a half plus a third minus a fourth plus a fifth minus a sixth and so on. That's what summation notation does. It says just do things in this order. And what we have to do is extra and realize that this will give us a sum, but we can't really be sure what it is. As long as we keep this order, then everything will work out fine. But if you start mucking with this order, you're going to start changing things. Any questions? This is a more abstract version of Star Trek, and it's all its weird timelines and going back to some other timeline. You know what I mean? You start making changes to here, and then it changes the outcome. Even though we don't think it should, because we grew up knowing this. Any questions? So we're still at the place. The game is still, given a series, is it absolutely convergent, conditionally convergent, or divergent? It's just multiple choice with 3 choices. So it's not quite true or false. 3 options. Absolutely, a series can be absolutely convergent, conditionally convergent, or divergent. Any questions? Comments? One of the reasons that we want to be able to look at the series and determine if it's convergent or divergent right away. The most important thing is convergence versus divergence. If we're getting into the weeds, then we care about conditional convergence versus absolute convergence. So the most important thing is to get one of these, convergence versus divergence. It's just like school. There's passing grades and there's not passing grades. Your first concern is to get a passing grade. Your second concern is to get an A or a B, or just a C. If at the end of the semester you get a C in a class, by definition, you need to be satisfied with that grade, because it says C, satisfactory. So you get a C in a class. I know most of your parents might tell you, you did bad in that class. You'd be like, oh no, by definition, I did satisfactorily. If you get a B, if you have those kinds of parents, if you get a B, then they're going to be, that's a bad grade. So I go, no, look at the glossary of terms. B, by definition, is a good grade. Getting good grades is a 3.0 by definition. You know what I mean? Parents have been such a bad influence, we had to start inventing grades above A. So I'd be like, oh, okay, your kid got an A. There's nothing else that I could have asked for. And then the kid sitting next to them also got an A. And their parents' egos got involved. Well, my kid never missed anything. Well, that is true. That kid missed some things sometimes. I go, yeah, but barely anything. I want my kid to have more. My kid should have a higher grade. And then so the teacher's like, oh, fuck it. Plus, I want to find out who that is. So I have some words for them. And after that, I got some hands for them. Fucking kowtow to some entitled asshole. Plus, put a plus there. I want a little gold star. You know what I mean? See, the difference was some of your parents didn't have enough money to just march down to the school and say, give my kid an A. So they took that anger out on you and got mad at you when you didn't get A's. Do you know what I mean? Meanwhile, they don't realize that they ruined the whole game at the very beginning because they said you were smart. If you want to ruin your kids when they're smart, tell them that they are. They're too young to have that kind of information. You know what I mean? Here's something I learned training dogs, and I think it applies. You get the behavior that you reinforce. Sometimes you don't realize what behavior you're reinforcing. If your dog still jumps up on the counter, you are reinforcing that behavior. You think you're not, but you are reinforcing that behavior because the dog continues to do it. At the very least, you're not reinforcing that behavior. Whatever happens when the dog gets up on the counter, you saying, no, no, get off and pushing them off is not enough to convince them. They still say, no, I'm still going to go up there. You know what I mean? So, anyway, you get the behavior that you reinforce. I forgot where I was going with that. So I stopped and started thinking about dogs, and then everything was off. What are we talking about? Oh, yes, that's right. This is where it came from. Your primary concern is converges versus diverges. Are we even going to get a finite sum? Because for the most part, when we encounter these, the order is set. We encounter a series, it's set with a certain order. So we're going to get the alternating that we wanted. So we can say, brrr, and everything's going to be fine. But then for detail's sake, we do still need to know the question, answer the question. When we have an infinite number of terms that results in a finite sum, when does the order matter? And here's one of the things that we need to know. Does the order matter? Ultimately, it doesn't, because the series that we're looking at has a determined order. So we really only care about convergent or divergent, finite sum or infinite sum. How's everybody okay? Is everybody worried because I think a C is a satisfactory grade? I don't know. I'm going to get murdered if I get a C. So if you recall, a power series had the form of a function in the form of an infinite degree polynomial. So we want to be able to look at a series and determine if it converges or diverges. Because when we get the power series, we plug a number into a power series. We're looking at a series, and we should know if that series means anything. Did we get a finite sum? So we have two different ways that we write power series, which is really just one. This is the way that I've been writing it so far. I've been centering my power series near 0. So we can also move the center somewhere else. And here we're just going to see the polynomial in terms of x minus a rather than x. Remember that the question for a power series is not, does it converge or diverge? The question is, for what values of x do we get a convergent series? So the question here is, for what values of x for what values of x do we get a convergent series? We know we're the things that we're looking for in a convergent series. We're going to think numerator versus denominator, factorials versus exponential versus polynomials. And we're just going to compare numerator and denominator. If there's a significant difference in power, a factorial will win out over an exponential. So factorial over exponential, that will diverge. The terms won't go to zero. Exponential over factorial, we would expect that to converge absolutely by the ratio test. If we see a polynomial over a factorial, the factorial is going to win. If it's in the denominator, the terms will go to zero fast enough to get convergence. There's nothing the polynomial can do to stop a factorial. I used to joke that I was going to buy the baseball team in Montreal. They're called the Expos. And I think it was for like the exposition. I would rename them for the Exponents. They'd still get to be the Expos, but it'll be short for Exponents. Like all their numbers, instead of being like big numbers set in the middle of their jersey on the back, it would be smaller and a little bit to the right. So they would be Exponents. And then my greatest hope would be somebody else finds another baseball team to be our rival and just calls them the factorials. And that would be awesome. And no one would understand why the factorials always win. Anyway, what are we talking about? Oh, yes. So we got to look at what's going on in our power series. We plug a number into for the x. This is going to make some kind of exponential term. And then there's stuff going on in the Cn. So it's Cn plus whatever exponential stuff we get for the x minus a to the n. So I recognize that x minus a to the n, that's polynomial stuff, but in terms of n, in terms of x, it's polynomial because the x is the base, but once we plug a value of x in, we're looking at a constant, the same constant in every term, and it's exponential in n. So we're going to have whatever is going on in Cn there's two places we're going to be looking for convergence. Whatever's going on in Cn, and in addition, some exponential stuff at x minus a. So we got to make sure that we got our factorials over exponential over polynomial, because that factor x minus a to the n is exponential in n. So there's always going to be some kind of exponential thing present. So where we look for convergence is we think about the ratio test. If the limit from the ratio test is less than 1, then we get absolute convergence. That's what we're going to focus on. So in this example, Cn is equal to n. X to the n part, that's making this a power series. But in this example, Cn is just n. If we want to know where a power series converges, we're going to run a ratio test. We're going to think about the ratio test. We could literally drop this series into a ratio test and work out what should happen. But we're going to start by thinking our way there first, rather than just robotically following PEMDAS, like a good robot. Imagine dropping this into the ratio test. This n part ignored. The ratio test doesn't care about polynomials. The ratio test will care about this x to the n. In the ratio test, we know that exponential, if that's the most powerful thing in your term, then the base of the exponential will determine convergence or divergence. Because when we get to the end of the ratio test, if we add 2/3 to the n, we get convergence because the 2/3 gets left behind. If we have 3/2 at the end, then we get divergence because the limit from the ratio test will be greater than 1. So the ratio test is going to ignore this n and leave behind the exponential parts. We're thinking about the ratio test. The ratio test is blind to this polynomial factor. And the ratio test will leave behind an absolute value of x. So if x is 2 to the n, you run the ratio test, we'll have 2 to the n. That'll go to infinity. But if x is a half, then we'll get a convergent series. So this series will converge so long as that absolute value of x left over from the limit from the ratio test is less than 1. If x is equal to 1, then the series looks like n. So if x equals 1, which diverges. If x equals -1, we get this alternating n, but the alternating is not enough. The terms don't go to 0. So that series diverges as well. So the endpoints both diverge. The absolute value of x less than 1 is the interval of convergence. The polynomial factors only come into play at the endpoints of the interval of convergence. At the endpoints of the interval of convergence, the limit from the ratio test is equal to 1, and the ratio test doesn't know what's going on. That's when we're going to start looking at the polynomial stuff. Because at that point, all the exponential stuff will have canceled out. Any questions? So I said we should be thinking about the power series when we're trying to determine the interval of convergence for a power series. We should think about the, I can't remember what sentence I just said. We're thinking about the ratio test when we're trying to find the interval of convergence for a power series. But that doesn't mean that we shouldn't, that we can't just run the power series through the ratio test to see what the limit is equal to. And that's also a perfectly valid thing to do. But it's the point of being in a math class to not have to do all the math anymore. You want to have run the power, so many power series through the ratio test that you can write down the interval of convergence without writing down the power series. You don't want to default to just do the mechanical thing. Does that make sense? I realize that for the most part, you're most successful in your math classes if you just learn how to do the mechanical thing over and over again, so that you can simulate that you know what you're talking about when it comes down to taking a test. But the point of a math class is to not have to do all that math anymore and to just know stuff. All right, tomorrow we'll continue looking at power series and finding the interval of convergence. That's gonna do it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.